welcome. We'll get started here in, excuse me, in just a second. We're continuing on in chapter 10, I believe, organic chemistry. So that should be where we're picking up. So again, we'll get started in a minute or two, picking up where we left off, chapter 10, organic. And again, as a reminder, if you do have any questions throughout the lecture, just feel free to ask them there in the chat box. Again, even if I've moved past it, feel free to ask. I'll be happy to go back and answer your questions if you do have questions. All right, so we started getting into organic chemistry, which starts here with chapter 10. And I believe it's chapter 10, chapter 11, chapter 12, and chapter 13, which is all organic. So as we talked about before in this class, essentially what that means is there's really not going to be any calculations. So for these chapters, you pretty much don't need to pick up your calculator or anything. It's really going to be more sort of memorization. So we're going to talk about how to name all these different organic compounds. We're also going to talk about different types of reactions. So you're going to have to figure out how to draw the products that you get when you have a certain type of organic reaction take place. So again, sometimes people like these chapters a little bit more because there's not so much calculations. And then again, some people like the calculations better than sort of the memorization part. So really we started talking about organic chemistry and really organic molecules. The bases of organic molecules are carbons, really attached to carbons. And really attached to those carbons are essentially hydrogens. And depending on what happens in an organic molecule, we will essentially kind of substitute out some of those hydrogens for other elements, things like oxygen, nitrogen are common ones. Sometimes the halogens there, group 7 on the periodic table, come in. Sometimes we create double bonds with these guys, single bonds, triple bonds. And by changing just these little aspects of these molecules, we get a wide variety of different organic compounds, or types of compounds. And the first little part here, this chapter sort of goes over all the different, what are referred to sometimes as functional groups, which represent different types of organic molecules. And then we'll get into really alkanes and all that kind of stuff here. We started, I think, at the end. By the way, organic molecules are essentially non-polar molecules because of that carbon-hydrogen bond is non-polar. And a lot of organic molecules are essentially nonpolar. As we, though, will see, some organic molecules are able to interact with things like water because although a vast majority of the molecule is nonpolar, they do contain sometimes some polar parts, and that allows them to, for example, interact with sometimes water. But we'll talk about those differences. Now, when we represent organic molecules, we sort of talked about some of the different formulas that we commonly will see in organic chemistry, some of which is on the screen here. But oftentimes when you draw out everything, kind of like what I drew out over there, where you really draw out all of the bonds to the hydrogens, for example. This is what is sometimes referred to as the expanded structural formula. So that's a very common sort of organic formula that we see, where you basically draw out everything. A formula that's very much like it, and this would be kind of the expanded structural formula over here, is a condensed formula. And in a condensed formula, we actually don't draw out all of the bonds to the hydrogens, but in usually most cases, we will still include that little dash between the carbons. And this is what's sometimes called the structural condensed formula, because you do include the dot, the little dashes. Some people may not include the dashes, like you can see here on the example here in the one where all the carbons go straight. They didn't really include the dashes, but most of the time people will include those dashes to represent the bond between it. Also, when we draw the sort of condensed formula like it's there, although it does appear that the bond is between the hydrogen and the carbon, it is actually between the carbon to the carbon. So what I'm talking about is like right here. If you kind of look at it, it may give you the idea that maybe the bond is between carbon and hydrogen, but it is actually not. That is representing this bond here, which is the bond between the carbon and the carbon. So when we do write in sort of condensed formula, we do sort of put it that way, but it's understood that the bond, sort of the backbone of the molecule, is that carbon to carbon bond. Now, when we have just pretty much a straight run of carbons in a row, again with all the hydrogens and so forth, this is what is sometimes referred to as a straight chain. And that's pretty much what it is. It's pretty much just a straight run of carbons together. And sometimes what we'll see as well, as we talked about, I think a little bit last time, and really what's in the picture above as well, is what is sometimes referred to as a branch chain. So sometimes you'll get this sort of branching that occurs off of the main chain. Oops, just a CH. Get rid of that. So you'll get this main chain, and then you'll have the branches to come off, kind of like on a tree. And that's what's sometimes referred to as a branch chain. So these again are two very common type of formulas that we see for organic chemistry. We will also see a little bit later on, but we'll just take a look at it as well. What is sometimes referred to as line structure is a very common sort of formula that's used in organic chemistry. And this is the one that maybe you've seen before. You just kind of like a mountain range sort of. And pretty much everywhere you see sort of a point, or everywhere where a line ends, it's assumed to be a carbon. So carbon would be here at the end, carbon would be here, carbon would be here, carbon would be here, carbon would be here, here, and here. So although it just looks like a sort of mountain range of, that's a really badly drawn mountain range, I apologize. Try that again. Good thing they have erasers, I suppose. All right, give it the old college try here one more time. Not sure that's any better, but we everywhere again there's a point or a place ends is a carbon. So carbon, as we talked about, a very essential feature of carbon is its need or want to make 4 bonds. So carbon always wants to make those 4 bonds. So when we see something written like this, it's assumed that all the rest of the bonds would be hydrogen. So if nothing else is written there, it would be assumed that all the rest of those bonds there would be hydrogen. So if we look at something like this guy would be a carbon, which then should have 1, 2, and 3 hydrogens coming off of it. This guy here is a carbon. It has 2 lines coming in, which would have 2 hydrogens. This carbon has 2 lines coming in, would also have 2 hydrogens. This carbon has 2 lines coming in, would have 2 hydrogens. And the guy at the end would have only 1 line coming in, which then would have also 3 carbons. And you can see very quickly why in line structure we typically do not include the hydrogens, because it gets really messy really quickly. And again, that's why usually line structure is just drawn pretty much like what we see here. Again, nothing else there, but it's assumed that each of those are carbon. So you pretty much could count everything and go, that's 1, 2, 3, 4, 5, 6, 7 carbons. There would be 3 hydrogens at the end, 2 in the middle here. So 2 is usually in the middle. So 3, 5, 7, 9, 11, 13, and 3 more gives you something like 16 hydrogens is what that would represent right there. Any questions on that? And again, you'll sometimes see line structure drawn, even a branch type thing. You'll sometimes just see a line just straight up. And the same thing at the end of this line would be a carbon, and it should have 3 hydrogens to get that carbon to, although it just looks like a 2 I made there, but that should be a 3. 3 hydrogens there to get that carbon to 4. Any questions on that? All right. So also, how I got the 16 hydrogens off of this guy up here is, again, it's the idea that that carbon wants to basically make 4 bonds. So in organic chemistry, you could almost safely assume if nothing else is drawn there, to get hydrogen to those 4 bonds, everything else is going to be, to get those carbons to 4 bonds, everything else is going to be hydrogen. So what I'm going to do here is just grab a different color so you can maybe get some contrast here. We'll go with red. So when we look at this guy at the end here, let's put a circle, okay? And that circle represents a carbon. There's only 1 line coming in, right? So 1 line would represent 1 bond, which means this carbon at the end still would have 3 bonds it needs to make. And those 3 bonds would be hydrogens. So I'll draw an H, 1, 2, and 3. Now, when we go to the next carbon, which would be at the peak there, this carbon here, again, I'm just going to draw it as a circle. And this carbon, though, has 1 line coming in, 2 lines coming in, which would also have 2 hydrogens to get it to 4. This carbon down here would also have 2 lines coming in, so it needs 2 hydrogens to get it to 4. This guy in the middle also has 2 lines coming in, which means it needs 2 hydrogens to get to 4 bonds. This guy, same deal, needs 2 hydrogens to get the 4 bonds. This guy here also has 2 lines already coming in, would need 2 hydrogens there. And the guy at the end only has 1 line coming to it, which then it would need 3 hydrogens to get the 4 bonds. And again, if you count all that, hopefully I didn't mess it up, but 3, you got, oops, but don't hit it, 3, 5, 7, 9, 11, 12, I think I messed up there, 11, 13. I'll learn to count soon. Hang on, try that again. 3, 5, 7, 9, 11, then 13, I think comes next, and 3 more gets you 16 in that particular case. So as we'll talk about in this chapter and other chapters, when you have to go to draw these structures, pretty much you want to start with just the carbon and carbons that are bonded to each other. And then to fill out everything else that's there, it usually will a lot of times be hydrogen. So you just want to get that carbon, each carbon to 4, and you can get it to 4 bonds by adding hydrogens. Other questions on that? Okay. Now, sometimes we do have a big run of carbons in a row, like what we have here, for example, and that's not a giant run in a row, but this is a repeating unit here of 2 CH2 units. So sometimes in the condensed formula, people will put a parentheses around a kind of repeating unit, and then the little number next to it to indicate how many of those repeating units there are. And as you can see, if you were to count this, this would be 1 carbon, 2 carbons, and then there's another one. So that would be 3 carbons and 4 carbons. And again, that represents the 1, 2, 3, and 4 carbons that you would have there. Here as well, they did it for a couple of these CH3s at the end. And again, these two guys here would be represented by that as well. So sometimes, especially a little later on in some of these chapters, you'll have some things, and even when we get into the biochemistry chapters, a big run of kind of repeatable units like the CH2 units, and very common people will sort of shorten that down so you don't have to write so many of those carbons. So the skeletal structure is also sometimes what is referred to as sort of the line structure, which is basically what we were talking about a second ago. So if we have something like this, again, if you have just a line like that, or if you have something like this. So the difference here between these two, when we look at it, just to make sure everybody understands how many carbons and stuff we got going on. If we look at it again, everywhere where the line ends or comes to a point is a carbon. So this would be a carbon. 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 Now, this lonely line that oftentimes confuses people, it's just like a line with nothing at the end of it. What's at the end of it is the same thing that it would be at the end over here. It is actually a carbon as well. Now, this one does actually have something written there, which means there is no carbon there. That's actually a bond between a carbon and a bromine. So in a line structure, if you see a line and there's nothing at the end of it, it is assumed that that's a carbon, and it probably will have 3 hydrogens attached. If you see a line in a line structure, like the bromine there, and something is written, then obviously that is what is attached. And the same rules we were talking about here, this guy has 1 line coming in, which means technically, I won't draw each of them separately. He should also have 3 hydrogens. This guy at the end also has 1 line coming in, which means he should have 3 hydrogens. Guy at the very top has only 1 line coming in, should also have 3 hydrogens. This guy has 1 line, 2 lines, and 3 lines coming in. He actually just has 1 hydrogen attached. This guy has 2 lines coming in, which means he would have 2 hydrogens attached to it. This guy here where the bromine is has 3 lines, which means he technically would have 1 hydrogen. Again, in line structure, we typically don't write any of those carbons like I just did. We typically don't write any of the hydrogens. Basically, in line structure, again, if you saw sort of the complete one, wherever my pen went there, there it is. So basically, it would look like if you saw this sort of line structure, it would look just like that. Obviously, nothing else written in there. And again, you do need to be able to understand when you see something like this, maybe a little nicer drawn. It does represent really something like this as well. Any questions on that there? So here's a couple of different ways. The left one is kind of the expanded structural formula. You could also do this over here, which is more of a line structure, where again, this guy on the right is the same thing as the guy on the left. Again, line structure on the right, just everybody drawn out on the left. You could even do a condensed structure, which would look something like this. Which would also look like this. So these are all basically representations of the same molecule. It has 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons in this guy. Each of those are basically the 6 carbons that we see. Again, not drawn there on that particular one because it is line structure. We want to count up how many lines are coming into each of those. So for example, coming into this guy, we got 1 line, 2 lines, which again would mean he would have, technically speaking, like we see on the left, 1 and 2 hydrogens at each of those carbons. Again, carbon and 4 bonds is really important to keep in mind when you're drawing these sort of structures. Also, like we talked about last time, important to keep in mind, not more than 4. So that is sort of the other problem that sometimes people do. They always want to put way more bonds to carbon than 4. Before you know it, sometimes carbon has got like 60 bonds to it. Probably not that many, but you know, people just keep on adding bonds to it. Again, this is 2 examples. This is more, again, a expanded structure over here, structural formula. This, again, is more a line structure. So you can see a line structure is really kind of bare bones. It's just kind of the basics there. You really only draw out different groups that make that molecule a little bit different. Again, the condensed formula would look something like this. And actually, it wouldn't look like that. I got 1 too many hydrogens there. Good thing there's an eraser today. And then we would have, so this guy again would be the condensed. This really would be sort of the expanded structural formula. And this would be the line formula. Again, each of these represent the exact same molecule. It's just basically 3 different ways that you could represent it and 3 very common ways in organic chemistry that you could represent it. So how do we get all these different organic molecules, different types of organic molecules? It is all based on what is referred to as a functional group. So in organic chemistry, there's always going to be a certain part of an organic molecule which basically makes it a certain type of organic molecule. So for example, the first few kind of simple functional groups, if you have something that is nothing but carbon and carbon single bonds, the carbon-carbon single bond would be the functional group for a class of organic compounds which are known as alkanes, A-N-E-S. If you take that single bond and somewhere in that molecule, you've got a carbon-carbon double bond, this would be the functional group for another type of organic molecules known as an alkene, E-N-E. If you turn that double bond into a triple bond, so if you see a triple bond in an organic molecule, that is the functional group for a group of organic molecules known as alkynes, Y-N-E-S. Just like we saw in the previous slide, actually, if you have an organic compound that has an OH group on it, that is also a functional group for another type of organic compound, which are known as alcohols. So when we look at all these different organic compounds, there will always be sort of a part of that molecule that basically is how you can classify it as a certain type of organic molecule. You could classify it, oh, it all has single bonds, it's an alkane. It has a double bond, it's an alkene. It has a triple bond, it's an alkyne. It has an OH group, it's an alcohol, is the functional group. So you do need to learn these different functional groups. We're going to go through sort of an overview of all of them, I think, in this chapter. And then for the rest of the chapters, we'll go into each one specifically and talk about each one specifically. Again, depending on the functional group that's there, these compounds will have some different properties depending on sort of what is in there. Sometimes functional groups are attached, and sometimes in organic chemistry, and even later on as well, you'll sometimes just see R. And R is sometimes used just as a generic form for basically the carbon part of the molecule. So for example, if I had, CH3, CH2, CH2OH, when I look at this molecule, I see the OH group that's there. That tells me this is a alcohol because that's a functional group. So again, sometimes alcohols in general will just be written like this, which essentially means this is the functional group. And this R represents the carbon part, maybe 1 carbon, maybe 2 carbons, 3 carbons, however many carbons. But sometimes sort of shorthand, when you look up sort of the different functional groups, that's sometimes how they are sort of labeled. So we talked a little bit about these guys here, the functional groups, but let's talk about them. First off, when we talk about organic compounds, sometimes some organic compounds are referred to as hydrocarbons. And pretty much what the name says is pretty much what it means. A hydrocarbon is pretty much a group of carbons attached to carbons and carbons that have hydrogens attached. So it's nothing but hydrogens and carbons involved. And those are what are known as hydrocarbons. So these are the first sort of 3 organic molecules or classes of organic molecules. Again, the functional group for an alkane is all carbon-carbon single bonds. If you have an organic molecule that has a carbon-carbon double bond, I'll draw it in there, at least one of those, it then becomes an alkene. You have a carbon-carbon triple bond like we were talking about on the other slide, it is an alkyne. No, so the R is not necessarily used only with the OH group. So for example, this group this part right here is the functional group. This part right here is the functional group for a bunch of organic molecules that are known as aldehydes. And if you're not really talking about a specific one, for example, is it 1 carbon, 2 carbons, 3 carbons? This part of the molecule over here is where somebody would write perhaps just R to represent that. This part of it is really, again, could be 1 carbon, 2 carbons, 3 carbons, is some type of carbon groups attached to that functional group. So that's really what the R represents, is that it is some type of carbon group attached. And again, it could be a 1 carbon, it could be 2 carbons, 3 carbons, 4,000 carbons. It's just kind of a generic way of representing a organic group as a whole. And just like that's just the carbon part of it. So it doesn't have to always be the OH. As you can see there, you could use it with something like an aldehyde or any of the other functional groups as well. Now, an aromatic hydrocarbon contains a benzene ring. So when we talk about aromatic organic compounds, it contains a benzene ring. And let's talk about what the benzene ring looks like. Benzene ring looks like this. It is a 6-carbon ring that has 3 double bonds in it. So it could look like this, or it may look like this. Double bonds over here. Or a lot of times people will just draw the benzene like this with like a circle in the middle. And that's because these double bond electrons are moving around. These are what are referred to, if you remember from bonding, resonance structures of each other. So those double bond electrons at certain times could be like this. They may be on the other side. So sometimes, and I think your book may do it, or a lot of books will do it, is they'll just kind of generically draw the benzene ring. And that's what this is up here, the benzene ring. All these guys. These are all examples of a benzene ring, which again is a 6-carbon ring. The difference, though, is when you have those 6 carbons, in this case, because we have those double bonds, say here, here, and here, we actually only end up with 1 hydrogen each because it already has 3 bonds to it. So we end up with just that 1 hydrogen at each of these places. So this carbon has 3 lines coming in, which means it gets 1 hydrogen, gets 1 hydrogen, 1 hydrogen, 1 hydrogen, 1 hydrogen, and 1 hydrogen. So when we talk about something that is a group of organic compounds that is an aromatic, it should contain this benzene ring. So again, I think most of the cases of what you'll come across it, again, a lot of times they'll just kind of show it like that. But truly, it could be like over here on the left. It could be like on the right over here as well. Now, out of these guys on the screen, truly for our purposes and most organic purposes, as we'll get into alkanes a little bit later, this guy right here is really the most important. The alkanes is really the most important ones. Every single organic compound, no matter what class of organic compound, they all come back to how we name the alkanes. So they're all based on the carbon-carbon single bonds. It's actually, this is actually the structural formula right here is for benzene. This is the line structure over here for benzene, any of these basically. So this is more the line structure. This would be kind of the structural formula. And again, the condensed formula would be something like this. As I run into the next guy, sorry about that. But it'll look something like that, basically. And to answer your question, yeah, so the condensed form would look like on top there, probably a little bit neater drawn, but it would look like the guy on the top. Yeah, so we're going to get into how to name and how to draw these guys in just a little bit here in this chapter. But there's really a lot of clues to kind of help you decide, how to properly name it. And all the names do come back, as we'll talk about, to the alkanes. And every other organic group is named just slightly different based on the functional group that's present. So it is named a little bit different. And we're going to talk about how those slightly different names come about. So this table, which is from your book, is all the different sort of functional groups that we'll come across. We talked about our alkanes, our alkynes, and our alkenes, our aromatic compounds, which is our benzene-containing guys. Here's some other organic guys that we will get to in later chapters. Alkyl halide has a halogen involved. Alcohols, as I talked about earlier, have that OH group. This is the functional group for an ether. And again, this is what the R represents. Really, it's a carbon, oxygen, carbon sort of connection that allows you to know that it's a ether. This is a carbon attached to a NH2, and that is an amine. This is a carbon that's attached to an SH, is a thiol. Again, all these are in the later chapters as well. They all have special names, and we'll go through each of these, and there's a lot more, and we'll see in just a second. Other kind of important groups that we will see in terms of functional group is this guy right here. This is what is known as a carbonyl group. And a carbonyl group is basically this part of it here. this carbon-oxygen double bond. And this is sometimes also referred to as the carbonyl carbon. And the carbonyl carbon is the carbon that has that oxygen double bonded to it. So that is something that we'll come across a lot. Here's some more organic groups, aldehydes like I drew before. Again, here's where we're using that R. And again, that R just really represents a carbon. This is a ketone, which is basically a 3-carbon run in a row with an oxygen double bond in the middle carbon. So that's how you know it's a ketone. And again, these are the groups that you want to look for to help you identify what type of organic molecule you're dealing with. And as we'll go through these chapters, there will be different ways to name them and deal with them. This is a carboxylic acid. The way you recognize a carboxylic acid is really this part, that carbon-oxygen double bond with the OH bonded to it. The ester is a carbon-oxygen double bond that has an oxygen connected to a carbon. So again, if we get rid of those R's and just put a carbon in there, this is basically what an ester looks like. Again, those R's represent some type of carbon group. Again, could be 1 carbon, could be 2 carbons, could be a bunch of carbons. And again, that's what the R is sort of used for. And then amide as well has a carbon-oxygen double bond and has a NH2 group attached, like what we see right here. This part of the molecule here is what makes it an amide. So you'll be able to recognize these different parts of these molecules as you start seeing them in these different chapters. And like I said, that will allow you to sort of have an understanding as to how to deal with it in terms of naming them, what type of reactions they occur and happen. Any questions on that? All right. So then let's get into actually some of these hydrocarbons. So let's start with alkanes. So alkanes, as I talked about, is the fundamental organic group. It is the one that has the functional group of carbon-carbon single bonds is our alkanes. And this is our functional group here. And as I mentioned before, it is the basis of how everybody is named. So when we learn these first 10 alkanes in just a second in terms of their names and their formulas, if you want to do well here in organic, the quicker you understand those first 10 names and their formulas, the easier everything else is going to be, because 100% of all the rest of the chapters and all the rest of the functional groups are based off of these alkanes. Alkanes have a general formula of CnH2n plus 2. So N is the number of carbons. So the simplest alkane you could have is CH4. C would be 1. 2 times 1 is 2, plus 2 is 4 hydrogens. That is methane. If we go to 2 carbons, 2 times 2 is 4, plus 2 is 6 hydrogens. This is what is known as ethane. If we go to 3 carbons, 3 times 2 is 6, plus 2 is 8 hydrogens. This is known as propane. You can get it right there. If we go to 4 carbons, 4 carbons, 4 times 2 is 8, plus 2 more is 10. And that will get us 10 hydrogens here. And that is what is known as butane. While we're going, we'll keep going. 5 carbons gives us 12 hydrogens, and that is what is known as pentane. 6 carbons, 6 carbons, 6 times 2 is 12, plus 2 more gives us 14. So 6 carbons, 14 hydrogens. That is what is known as hexane. Again, please, thank you. 7 carbons, 7 times 2 is 14, plus 2 is 16 hydrogens. That is what is known as heptane. 8 carbons gives you 18 hydrogens. That is known as octane. 9 carbons, 9 times 2 is 18, plus 2 is 20. That looks like a 30. Let's make that a 20. That is nonane. And lastly, C10H22 is decane. So these first 10 alkanes are super important because every single organic molecule will come back to these 10 names. So it's really important to know the name, to know how many carbons are involved. And although it's written in just the molecular formula here, the same connection as we've been talking about is what happens. It is carbons to carbons, and hydrogens attached to those carbons is how these are connected. So if we look at this here, and we count it, that is 3 carbons and 8 hydrogens. That is propane. So this is the molecule for the structural formula for propane. If we did the line structure for propane, it actually would look like that right there. 1, 2, 3 carbons. Yeah. We did the condensed formula for propane. CH3, CH2, and CH3. Yeah. So that would be the condensed formula there for propane. Again, all represent propane, including this way, which is just the molecular formula. It's not a structural formula or anything like that. It's just the molecular formula. These are all alkanes, which means that they have all carbon-carbon single bonds. They all fall under the group of alkanes, which means if you look how every single one of these end, they all end in ANE. Yeah? And that is to tell that it is an alkane because they end in ANE. They all have carbon-carbon single bonds, just like the big group there is alkanes, ends in ANE. Each of those ends in ANE. Any questions on that there? These are also sometimes called saturated alkenes or saturated hydrocarbons. And they're saturated hydrocarbons because when you look at each of these carbons, they have the maximum number of hydrogens they could have. So when you have all carbon-carbon single bonds, they are what are known as saturated hydrocarbons because they contain the maximum number of hydrogens that a carbon could have. Right. Any questions on that there? So here's our condensed formula. By the way, when you look at this zigzag shape, when you kind of do a line structure or a structure like that, it is a zigzag shape because of a very certain reason. It is zigzag because if you look at, we'll just take a look at this carbon here. If we go back to our Lewis structures and molecular geometries, if we look at this carbon right here, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Also has 4 bonds. So the geometry that we see at this carbon, and actually all these carbons have 4 electron pairs and 4 bonds, is that tetrahedral geometry. And it's because of that geometry that we often will draw that line structure in what is sometimes referred to as that zigzag pattern. Because of the tetrahedral geometry, it creates those molecules that kind of have, again, usually referred to as like a zigzag sort of shape. Now, there also are alkanes, which are single bonded alkanes, are single bonded structures, but they will basically take both ends and connect them. And these are what are known as cycloalkanes. So cycloalkanes are basically ring structures. And they're basically still all carbon-carbon single bonds, but the difference is basically both ends come together to make a ring. And the common ring ones that you see is usually drawn in line structure. You have your triangle, you got your square, badly drawn square. You got your 5-member guy here. Actually, I'll make him 6 because I misdrew it. We'll make this guy 5, I think. There we go. Things like that. So this is our 3-member ring, 3 carbons. This is 4 carbons. This is 6 carbons and 7 carbons, 5 carbons. And again, usually these guys are drawn with line structure. Usually don't draw too much of the condensed, but you could. But usually they're just line structures. But same rule, even though they're kind of a ring, there's a carbon there, carbon there, carbon there, carbon here, carbon here, carbon here, carbon here, carbon there, 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 and there. And this guy, carbon there, carbon, carbon, and some carbons there. So usually these guys are drawn in sort of ring type structures because they actually close the ring. In order to make a bond, essentially in organic chemistry, sort of remember, when you make a bond, you actually have to lose usually 2 hydrogens when you make that bond. So when we draw our 3 carbons in a row like we had on the previous page, which is our propane, in the straight form like this, it's got your 3 carbons and your 8 hydrogens. But when these 2 carbons come together, this hydrogen here and this hydrogen here, for example, are lost. Otherwise, it would have too many bonds, and it comes together. I'll draw it in the condensed formula, like so. And this guy has 3 carbons still, but now only has 6 hydrogens because we had to kind of close the end in on itself to make that bond. So we did lose 2 hydrogens in that case. And when we name these guys, surprisingly enough, this guy is known as propane. And since these are cycloalkanes, when we have something like our triangle, although it is 3 carbons, it's still propane, but because it is a ring structure, we call it cyclopropane. So this would be cyclopropane. The ring doesn't necessarily lose the 2 hydrogens. Kind of the straight guy here, the straight chain, in order for it to kind of close up on itself, it has to lose those 2 hydrogens. And just to show you, if you didn't lose those 2 hydrogens, for example, you would have something like CH3 here. You would have like CH3 here and like CH2. The problem here, though, is if you really did have those 3 hydrogens still there, along with the bond going this way and the bond going this way. My carbon now has 1, 2, 3, 4, 5 bonds, too many bonds. So what happens is as that guy goes from, cross that out too, as the guy goes from kind of the straight chain to this kind of closed ring structure, in order to do that and maintain the correct number of bonds, you always lose basically 2 hydrogens. It also happens when you put on like a double bond or a triple bond, you actually lose some hydrogens along the way. And every time essentially you put 1 bond together, you have to basically sacrifice 2 hydrogens to do that. Otherwise, you'll end up with too many bonds. So this guy, which has 4 carbons over here, is in this straight form butane, but because it's a ring, it would be cyclobutane. They're actually just lost as H2. They just come off in a reaction, which is known as an oxidation reaction. It's actually just removed, and they come off as just H2, like hydrogen gas, sort of. It's just sort of removed that way in the process. This guy right here, which has 6 carbons, is known as cyclohexane from hexane. This guy with 5 carbons, which is based off the pentane, would be cyclopentane. Yeah, so in the ring structure, it's the same name as the straight structure, except that when it's in this ring structure and it closes up on itself, it will just put the cyclo in front of it. So like I said, the 3 carbon there in the straight version is propane, like we have on the right. When it closes up on itself and makes sort of a ring structure, you just put cyclo in front of it and it's still propane, again, because it's still the 3 carbons. Other questions on that? And just like each of these here, if it was in a straight chain, it would be butane. This guy would be hexane, and this would be pentane. So I think it was maybe on the last slide. Yeah. So those ones that we just folded up, pentane would just be 5 carbons in a row, but when it folds up into that ring structure, it becomes cyclopentane. Hexane is just 6 carbons in a row, but when it folds up into that ring structure, it becomes cyclohexane. Yeah. So here's those names that we were talking about. Again, really important to get a very good understanding in terms of these names, because it's going to be all about the naming. Everybody comes back to the naming. And usually when we name things, we go by this name right here, which is sometimes referred to as the IUPAC name. That's the International Union of Pure and Applied Chemistry. I'm sad that I know that, but that is usually kind of the official name. Those are the guys that come up with all the names for the elements, all those weird rules that you had to name everything. The IUPAC is sort of the guys that come up with all these sort of rules. So we went through these on the other slides, so we won't go too long with these here. But again, these are the first 5 alkanes. And this, again, is more of the condensed formula over here for each of them. Even though it says structural formula, it's actually the condensed formula for each of them here. So that's actually the condensed, really, over here. So methane, again, is a 1 carbon. It's the simplest organic molecule you could have. It is, what comes out when you light a Bunsen burner. And again, it has that tetrahedral geometry with 4 electron pairs and 4 bonds, which again is really what gives those alkanes that zigzag sort of shape that we see. Is everybody in there with the single bonds all have that tetrahedral geometry. Ethane, again, is our 2 carbon one. So this is our condensed formula. That's our structural formula. That's our model formula. These guys represent one coming forward and one coming backwards in 3-dimensional space. That's what the wedge and kind of the checkered line sort of represents. Like this is supposed to be coming out of the board and it's supposed to be going backwards, in 3-dimensional space. There's our propane, again, our condensed formula, our structural formula. You can see the connection is carbons to carbons, and again, hydrogens here. These are all saturated hydrocarbons. They all have the maximum number of hydrogens there all the way around. Now, when we have the following ones are both propane, and sometimes you're going to be asked to draw isomers, or if these things are isomers. So let's just talk about isomers for just a second here. An isomer, for example, is basically the same molecular formula, but different arrangement of those atoms. So for example, these are 3 carbons in a row. And you may look at both of these and go, they're different. They definitely look different. But one thing that we'll talk about is when you go to name compounds, the first thing that you should always look for is really the longest carbon chain. And when you're looking for the longest continuous carbon chain, that helps you really basically name it. So when you would look at these guys, we would look at and try to count the longest continuous chain here. So when we're counting it, the rule is you can't go backwards. You got to start one way and end. So this would be 1, 2, and 3 carbons in a row. Everything else is hydrogens. So this is propane. Now, when we look at this one, although it may look like something different, this is 1, 2, and 3 carbons in a row. The longest continuous carbon chain does not always have to be the straightest. So it doesn't have to be the straightest. The only rule is you go one direction, could go down, but you go one direction and stop. You can't go like down and then come back up and go backwards and then go this way. You can't like back around anything like that. You can go in one direction until you kind of hit a stopping point. So even though this may look different to you, this is also still propane. It's just drawn with a bent. It's the exact same thing. Now, what an isomer is, for example, is let's say we had this guy. And let's say we had this guy. And while we're here, one more guy. All right. So let's take a look at each of these here really quick and sort of see what we got going on here. Okay. Let's just switch a color here so we can see it. Yeah, I'll go with this color, I think. Let's first count up how many carbons we got and hydrogens in each of these. This has 1, 2, 3, 4 carbons. It has 4, 4, and 10 hydrogens. Let's take a look at this one. It has 1, 2, 3, 4 carbons. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. This guy has 4 carbons and also has 10 hydrogens. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and I missed one there when I was drawing it. Let's put it in 10. There you go. Now, they all have 4 carbons and 10 hydrogens. And to yourself, you may say, they all kind of look different. Perhaps they're all isomers of each other. So let's take a look and trying to think about the longest carbon chain. So if we look at this guy here, longest carbon chain is 1, 2, 3, and 4. Nothing else is attached, all hydrogens. So 4 carbons is butane would be the name of this. Now, when you come to this guy right here in the middle, you may again say, looks like a different structure. It definitely is. So let's count how many carbons in a row. This is 1, this is 2, this is 3, and this is 4 carbons in a row. Nothing else attached. This is actually still called butane. Again, you just drew it down instead of straight. These are the same guys. And they are not isomers of each other. So they're not isomers here. Again, they're just different ways to draw it. So sometimes when people want to draw isomers, they'll go, oh, I'll just draw the end down or I'll draw the end up. And it's really not a different compound. It just looks different because of the way you drew it. And the best way as we get going into this to figure out if you actually did draw an isomer or not is to name it. And if you end up with 2 different names for the guy that has the same formula, then you did draw isomers. So let's take a look at this last guy over here on the right. And if we look at this last guy on the right, it has it has a bad color choice here. Let's try that again. Yeah, we'll go with no, there we go. All right, so it has 1 carbon, 2 carbons, and 3 carbons only in a row. You also could, if you wanted to, count it this way. Again, we can't go backwards. We have to go one way until we hit a dead end. You could go this way. 1, 2, and then go up would give you 3, but still only giving you 3 carbons no matter which way you go. So now when we go to name this, this is based off of not 4 carbons as the longest carbon chain, but it's based off of 3 carbons. And if you remember back to our 10 alkanes, something with 3 carbons is propane as the base of the name. Now, when we look at this guy, he has some other things going on here. So what I'm going to do is I'm going to redraw it up here just so we can kind of see what's going on. And I'm just going to draw it in the condensed way to sort of save some room. So this is the exact same guy that we're dealing with at the bottom. So if we take the longest carbon chain, which is what you should always do when you go to name something, is you want to find the longest carbon chain. In this case, we could get to the longest carbon chain 2 different ways, like we did on the bottom, actually 3, I guess. But I always find that it is best to take sometimes just the straightest. And when we take the straightest, longest carbon chain, it should match one of those 10 names of the alkanes. So it should match methane, butane, propane, ethane, hexane. So again, when we get the longest carbon chain, that's going to become the base of our name. So the base of this name would be propane. Now, when you look at this guy, what we see is outside of the main carbon chain, there's actually something else that's hanging out. And what we have up here is a CH3. What we essentially have when you have something like that that is hanging off the top there or off of the main chain, these are what are referred to as groups, and they're sometimes referred to as alkyl groups. And these are guys that are part of the structure, but not part of the longest continuous carbon chain. Now, these guys are really referred to as alkyl groups, ends in YL. These guys as well are still based off of those first 10 names. So when we look at this CH3 group, it has one carbon. And if you remember, the one carbon alkane is methane, ANE. This does not have four hydrogens. It doesn't have four hydrogens because if it had four hydrogens here, you would have too many bonds. So when it becomes a group, it loses a hydrogen to allow it to bond to the chain. And it's actually named based off of methane, except that it's an alkyl group, which ends in YL. So this becomes, from methane, this becomes a methyl group. And the name of this guy would be methyl propane. And not necessary really in this molecule, but we also will number this chain. So this carbon's carbon 1, that's carbon 2, that's carbon 3, in a way where we can get the smallest number for those groups. This is not really necessary here because there's only one place where that methyl could go. It could only go on the second carbon. But, you know, I'll just put it here, 2-methyl propane, but it's really not. It's really probably just going to be called methyl propane in this case because it can only go in one spot. So to get back to the isomers, and we're going to talk about naming a little bit more here in just a second, but to get back to our isomer situation, when we go through this process of naming, we see that we do get a different name here than what we had down here. And although they have the same structure, not structure, but the same molecular formula and a different connectivity and a different name, that means that they are isomers of each other. So this guy over here, which is methyl propane, this guy and this guy are isomers of each other. This guy in the middle is the same as this guy, not an isomer. We're going to talk about numbering in just a second, so we'll get to it in a couple of slides, I think, on how to name everything and kind of work that out. So just hang on tight, and we'll get there. All right, any questions on isomers? So the important thing about isomers, and again, it gets a little bit easier as you start naming things because you'll be able to, that's really the best way, because sometimes you draw something and you look at it and go, it looks different, so it's probably an isomer. But when you get to the naming part of it, you could really tell if you end up with the same name, they are not isomers, but if you end up with different names, they are going to be isomers. All right. So here's butane, and there's our 2-methyl propane, which is our example here that I just did. And again, they do include the 2 here, so you can include the 2. The 2 is really just the location, and naming is really all about location. In the name, you're essentially telling everybody where you could find all these things on the compound. And so butane, this is the straight chain. This is 2-methyl propane, which again, you can include the 2 there. And again, these would be isomers of each other. And that's what I talked about it just a second ago. Isomers have the same molecular formula, but a different connectivity. Same thing here. If we count up everything here, we got on the guy on the left, We have 1, 2, 3, 4, 5, and 6 hydrogens. 1, 2, 3, 4, 5, and 6 hydrogens. We have 2 carbons, and 1 oxygen. This guy, the way it's connected here, is an alcohol. You might be able to kind of see the naming here. This has 2 carbons, which is based off of ethane, but it's an alcohol, so ethane becomes ethanol, right? OL, OL. That's sort of how these things are named. This is 2 carbons, which is based off of ethane, but it has this is the functional group here, which as we saw earlier is that carbon, oxygen, carbon, which is your ether functional group. This is actually a common name for an ether. This is what is known as dimethyl ether. So these are 2 isomers of each other, different connectivity. And here is pentane, and again, some different connectivity. If we're counting our longest carbon chain in each of them, this has got 5 in a row. The longest carbon chain here is 1, 2, 3, and 4, or you could go 1, 2, 3, and 4, and that's where this name comes into play. This is 2-methyl butane. 4 carbons in a row is based off of butane. It's the longest carbon chain. Longest carbon chain here, 1, 2, and 3. You could also get to it 1, 2, and 3, or 1, 2, and 3 going upwards. 3 carbons in a row is propane. Again, this is the location where we find the different parts there. So we're going to go through how do we get to each of those names here in just a second. Here's the rest of the 10 of the alkanes that we saw earlier. These are the condensed formulas for each of them. So let us talk about naming these guys. So the IUPAC way of naming is usually the way that you want to name these guys. And it is based off of really sort of the standard way of naming it. And there's really sort of these rules that you want to follow when you go about naming them, and we'll just go through them. There's the parent name, the suffix, and the prefix. It sort of tells us where everything is located. So the suffix is how we change the last part of the name based on the functional group. The parent name is the longest continuous carbon chain. And the prefix is, again, the groups that are attached. So groups that are attached are sometimes referred to as substituents. These are groups that are basically attached to the longest continuous carbon chain. Let's just try to get to one here. Alkyl groups are, as I mentioned earlier, just a second ago, are basically based off of the 10 carbons, but they are missing 1 hydrogen. And again, that 1 hydrogen allows them to connect without having too many bonds. And again, if they're an alkyl group, because they're an alkyl group, they will change the name from the alkane from ANE to YL. So taking a look here, that's our methyl group. Again, missing the hydrogen here, that's where it's able to connect in. This is our 2 carbon group, which is based off of ethane, missing that hydrogen, which allows it to connect in. There are some special groups, and probably the one special group that you need to know is this one here. This is CH3, CH3. The connectivity is happening right here into the main group. This is what is known as I'll get it right, come here. Isopropyl. That's the isopropyl group, basically. And it's based off of propane, which looks like this. So it is based off of propane, except that it is missing a hydrogen here. And that is different than a propyl group, because you could also have a propyl group. Let me just see if that's on the next slide. It is right here. We'll take a look here. So if you look at this guy here, these are our alkyl groups. This one right here is a propyl group. And that is different than what the one I just drew, which is this one, where the connectivity happens here, which is an isopropyl group. So really, what is the difference? It is actually where it's connected is the difference. When we look at propane, for example, there are what we call different types of carbons, and the different carbons are what are referred to as being primary, secondary, or tertiary carbons. Primary carbon, secondary carbon, are a tertiary carbon. And basically, a primary carbon, the carbon's attached to one other carbon. The secondary carbon, the carbon you're looking at, is attached to two carbons. And a tertiary carbon, the carbon is attached to three carbons. Yeah. So that's the easiest way to determine what type of carbon you're dealing with, is to look at the carbon that you're dealing with and see how many carbons are attached directly to it. So again, here, this carbon is attached to just one. The guy in the middle is attached to two carbons. The guy in the middle is attached to three carbons. Gives you a primary, secondary, tertiary. So if we look at this carbon, this is a primary carbon. This carbon is attached to just one other carbon directly to it. This carbon at the end over here is also a primary carbon because it's attached to directly one other carbon. When we look at the carbon in the middle, though, the carbon in the middle is attached to not one carbon, but this carbon in the middle is attached to one carbon here and two carbons here, which means that this carbon is what is known as a secondary carbon. So the difference between a normal propyl group, which sometimes people call this N-propyl for normal propyl, is that the attachment point is through the primary carbon, while on the isopropyl connection, it is connected through the secondary carbon. So that is the difference between those two groups, even though they're both based off of propane. One you connect through the primary carbon, and one you connect through the secondary carbon. So primary, secondary, tertiary carbons, you look at the carbon you're interested in and just count how many carbons are directly attached to it, and you'll be able to determine if it is, again, primary, secondary, or tertiary. All right, here's some other groups, not from your book, but really for us, the isopropyl one is the main one that you probably need to know. All right, so let us start actually naming something here and figuring out how to name it. So let's go with this one that we got here. And let's talk about how we would go about naming this guy. So the very first thing that you want to do is you want to find the longest continuous carbon chain. And again, it doesn't have to be the straightest. It could go up, it could go down. The only thing is you cannot go backwards. So whichever way you start, right to left, left to right, you got to keep going until you hit a dead end. So when we look at this guy here, we have 1, 2, 3, 4, 5, and 6 carbons. We could also go 1, 2, 3, 4, 5, and 6 upward as well. So if you start up on top and go to the right, you got 6. And those are the two ways that you could go. If you start at the top and you come down and go to the left, that's 1, 2, 3, which is smaller. So like I said before, if you have multiple options as to, where the longest carbon chain, sometimes it's easier just to take the straightest one. So like they did here, you could put a box around it. Can it still be I'll get back to you in just a second on that question, okay? So what you want to do is put a box around it like they did. And that longest continuous carbon chain, it will match up with those first 10 alkanes. So 6 carbons, the base of the name is going to be hexane, ANE, because they're all single bonds. Now, when we look at this, there is a group that's attached that is not part of the longest continuous chain. So here is our group. It is a 1 carbon group, which again is based off of methane. And remember, the groups have 1 less hydrogen, and they go from ANE to YL. So this is a methyl group. Okay. Now, once we identified the groups that are attached, once we identified the longest continuous carbon chain, the next thing that you want to do is number the longest chain. So there are 2 ways that you can number this, and we're numbering the carbons. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Alternatively, we can number it starting the other way. Go with green that way. And if we start at the other end, this would be carbon 1, this would be carbon 2, this would be carbon 3, this would be carbon 4, that would be carbon 5, and that would be carbon 6. So there are 2 different ways that we can number this chain. And the way that you want to number it is whichever way gives the group that's attached the smaller number. So when we look at this, if we go the blue way, our group is at carbon number 2. If we go the green way, that CH3 group would be at carbon number 5. And it is as simple as 2 is smaller than 5. So the way that we should number these guys is the blue way here, because it gives us the smaller number for the group that is attached. Any questions on the numbering? So there will always be 2 ways that you can number the longest carbon chain. You want to number it whichever way gives the group the smallest number. So it's always the smallest number, and that's always the way that you want to number it. So that means that at carbon number 2 dash, there is a methyl group, and this would be known as 2-methylhexane. Naming is all about location. You're basically telling people if you go to carbon number 2, you will find a methyl group connected to 6 carbons in a row, is essentially what that name means. Now, when we name these guys, between a number and a letter, we put a dash like we did here. So that's why there's a dash here. If you have 2 numbers that go back to back in the name, which can happen, we separate those numbers by a comma. So number to letter is a dash, number to number is a comma. Question on how to name that one there. All right, let's take a look at another one here before we call it for tonight. Let's just find one here. Let's find a better example somewhere. All right. Same one. 1, 2, 3. There it is. Okay. All right. So why don't you try this one real quick? Take a minute or 2 and give this one a go. And we'll talk about it in just a second. So see what you come up with. All right, so let's see just sort of how we're doing here. Again, you always want to start with the longest carbon chain. So if I go left to right here, I got 1, 2, 3, 4, 5, 6. If I go starting at the top here, 1, 2, 3, 4, 5, 6. If I start at the bottom, 1, 2, 3, 4, 5. So that's less. If I start at the bottom, 1, 2 to the left, 3, 4, and 1, 2, 3, 4. So it does look like 6 is your longest continuous carbon chain. Again, if you have that option, you might want to just take the straightest there. So that's 1, 2, 3, 4, 5, 6. So those 6 carbons in a row automatically tell us it is based off of hexane, right? Because there's 6 carbons. Now, again, once we've identified the longest carbon chain, we want to identify the groups that are there. So over here, we have a 1 carbon group. So that, again, is going to be a methyl group, YL. We also have another 1 carbon group over here, which is also going to be a methyl group. So we have 2 methyl groups. When you have 2 or more of the same group in a compound, you actually use prefixes. So 2 methyl groups would give us dimethyl. Di because there's 2 methyl groups, not necessarily on the same carbon, but in that entire molecule. If we had 3, we would call it trimethyl. If we had 4, just like the prefix we use for naming, it would be tetramethyl and so forth. So, you would use the same sort of prefixes. We do need to number this chain. So again, if we went left to right, this would be carbon 1. This would be carbon 2. This would be carbon 3. This would be carbon 4. That would be carbon 5. And that would be carbon 6. Now, if we went the other way, starting on the right-hand side, this would be carbon 1. This would be carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So if we go with the blue way here, we would have a group at carbon number 4 and carbon number 5 if we went that blue way. If we went the other way, whatever color that might have been, I'm not sure where I grabbed that from. If we went the other way, we would have a group at carbon number 2 and carbon number 3. The way that we should number this is this way. That is the smaller number. Again, it's as simple as 2 is smaller than 4. Yeah. So that is the way we want to number it. Now, in this case, we do need to give the location of where you can find each of those methyl groups. So this would be called 2, 3, comma between 2 numbers, dash dimethyl for the 2 methyl groups, dash between a number and a letter, comma between 2 numbers, hexane. So 2,3-dimethyl hexane would be the name. And again, basically means that if you go to carbon number 2 and you go to carbon number 3, you will find a methyl group at each of them off of a 6 carbon in a row chain is basically what that name means. Question on how to name that. I know we're running a little bit long, but I just want to talk about how you go from the name to the formula, and it'll just take a second. Yeah, there really is no space between the dimethyl hexane. You could run them together. In that case, there's no space. So let's just talk really quick if we had a name, and then I promise we'll call it done for the lecture today. But let's say we had a name. Just trying to find somewhere where I could maybe draw this. That's good. They got the same name. That's good. You know what? I'll just draw it here, or we'll do it here. Let's say we had this name of, let's see, let's do Let's do 2-ethyl 5-methyl. I'm just making this up, so give me a second here to make sure I have enough carbons. Let's go with octane. Okay. And again, I just made this up, so we'll hope for the best here. May not be perfect, but we'll try our best here. So when you have the name, and always when you're given the name, the way that you want to do it to draw the formula is you want to work backwards. So you want to start at the end of the name and work your way backwards until you pretty much have put everything on there. So when we do this, we're going to start with the back part of the name, which means octane, which now I'm regretting my choice because octane is 8 carbons. And at the beginning here, that is all you should draw is just the carbons. So you want to draw just 8 carbons in a row. Now I'm really regretting my choice. 8. I think that's 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So essentially, that takes care of that part of the name. Now, the beauty of you drawing it is you can draw it whichever way you want, which means you could call on this side, on the left-hand side over here, you could call this guy carbon number 1 and go 1, 2, 3, 4, 5, 6, 7, 8. And also because you're drawing it, you could decide I want to go this way and call this guy carbon 1, 2, 3, 4, 5, 6, 7, 8. So you have sort of the choice as to which way you want to number it because you're drawing it. I'm going to go left to right. So I'm going to draw it left to right, which means that this is going to be carbon 1. And you don't necessarily have to put the numbers here, but I'll put it here so you could follow along. All the way to carbon number 8, okay? So what the next part of the name means is when I go to carbon number 5, I should find a methyl group there. So carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. You could draw it up on top. You could draw it on the bottom. Doesn't matter, just as long as it's attached to carbon number 5. That takes care of that part of the name. That means what's left is over here. And this name means that when I go to carbon number 2, I should find an ethyl group. Now, ethyl is based off of ethane, right? That's how we get to ethyl. And ethane is 2 carbons. So this is CH3, CH2 group attached. Yeah? And that means when I come to carbon number 2, I will have a CH2, CH3. CH3 has to be at the end here. The connection has to be to this guy. Because if you drew it like this, that would imply that this carbon now has like 5 bonds, which is too many bonds. So the CH3 does have to be at the end there. That takes care of this part of the name, right? So what is left here? What is left is we need to fill in everything else as hydrogens. Now, this is where the importance of what we talked about earlier, carbon needs 4 bonds. So when we look at this carbon at the end, it only has 1 line coming in, which means he needs 3 hydrogens. This carbon has 1 line, 2 lines, 3 lines, which means he actually just needs 1 hydrogen. This guy has 1 and 2, which means he needs 2 hydrogens. This guy also has 2, which means he needs 2 hydrogens. This guy will only need 1 hydrogen. He will need 2 hydrogens. He will need 2 hydrogens, and he will need 3 hydrogens at the end. Again, everything else is hydrogen, so to redraw it a little bit easier to see, we will end up with something that looks like this. and right there, CH3, and right there, CH2, CH3. So that is sort of the order at how you want to draw these things. If you are going from the name to the formula, you always start at the back. You draw what's sometimes referred to as just the carbon skeleton, just all the right carbons. And then you can number it left to right, right to left, because you're drawing it. And then you attach the groups to the appropriate carbons. By the way, once you choose, for example, like I did, going left to right, that's carbon 1, you can't change your mind. You got to keep everything going in that numbering scheme from left to right. And then everything else, once you've attached all the groups, will be hydrogens until each of the carbons will end up with 4 bonds. As crazy as it sounds, I personally think that the drawing the structure from the name is the easiest one, because it actually tells you what to draw if you kind of work your way backwards. All right, any questions on going from the name to the structure? Okay, so I think we should stop here probably at this point. We'll do some more, obviously, examples of naming and stuff, and reactions that involve alkanes next time. We'll get into alkenes in the next chapter and some other stuff as well. How do we get this CH2, CH3? Are you talking about the ethyl group? This guy up here? Yeah. So what we had was the name ethyl. And remember, when we see the YL, that's basically those groups, which means it's basically based off of the alkane, but it has 1 less hydrogen. So if you get rid of the YL and put ANE back on it, that's ethane, which is CH3, CH3. So the ethyl group would be missing one of these hydrogens to allow it to connect. And that's how we get to the CH3, CH2, because it's based off of ethane. But again, it's the ethyl group, so 1 less hydrogen than the alkane to allow it to connect in. Other questions? Okay. So we ran a little long today, so we'll take a little break here, maybe 10, 15 minutes, and then I'll start the discussion. And if you have questions, feel free to drop by and ask. We'll be there for a bit. And if I don't see you, I will see you next week, I think. Yeah. Have a good weekend. And hopefully I can do my best to try to get those exams graded by sometime next week. And I'll let you know when they're graded, obviously. All right. Have a good weekend if you're out. And again, discussion will start maybe about 10, 15 minutes. Thank you, too. Alan, let me read what you wrote there. Yeah, so the difference is in the isopropyl. It's this secondary carbon where it will connect into the actual longest carbon chain. And that would be your isopropyl group, while your normal kind of propyl group, the connection would occur at the primary carbon. And that's where it would connect into the longest carbon chain. So it's really just the difference between sort of how, on which carbon it's able to connect into, you know, a longest carbon chain, basically. So if you had like a big chain of carbons like this, the isopropyl would connect to that second carbon, like that, as opposed to, again, if you had like a long carbon chain, the normal propyl group would connect at the end, like that. So it's really just a difference in how they're connected, which gives sort of a different group. The top right being the normal propyl group, the bottom middle there being the isopropyl group. So if you're asking, does it matter if the group is connected up here, or if I drew, say, the group down like this? It doesn't matter. None of the groups matter. So for example, you know, if you had a methyl group drawn up on top, and if you did like the same methyl group on the bottom, it's the same thing. It just doesn't matter if you draw it up or down on any of these groups. You know, maybe methyl's not the best, but if you had like say a bromine, you could draw the bromine up on top. You could, if that was the same carbon here, you know, put it on top. The main thing is, if this was, say, carbon number 2, and this was carbon number 2 in the same molecule, what's the important part is this bromine, whether you draw it on top or the bottom, it's on carbon number 2, for example. If that's, you know, where the bromine is supposed to be. That's the important thing, would be the carbon number. It doesn't necessarily matter if you draw it kind of on the top or the bottom, because it's really the same thing, because that molecule could essentially just kind of rotate. So if you just rotated it, you know, around like in a circle, it would go from the bottom to the top, or the top to the bottom. So the important part is that those groups end up on the correct numbered carbon. And again, it doesn't matter in terms of your picture which way you draw it. I didn't. I just drew it on a different carbon on the bottom, so it's the same. I just was just talking about. I was just asking if that's what you're asking. Could you draw the group on the bottom versus the top? Yeah. If I were to draw this the way I had it, I could have drew it on the bottom. Yeah. It didn't move carbons or anything like that. It would stay on the same carbon. So again, if you had this, say, 3 carbons, and you drew it like this, with obviously all the other hydrogens, this should be there. Or if you took those same 3 carbons and you drew it like this, it's the same thing. You do it either way. You're welcome. All right, I'm going to stop this meeting and then we'll start the next one for this. Try to stretch and stuff like that. So we'll start in about 10 minutes or so if you have more questions.